Hi, Physics 2. This is Mr. Janowski. This is part 7 of the chapters 15 and 16 slides. So here we're looking at this aerial photo, this big ring there. Yeah, that's not superimposed. That's actually there. So what are we looking at here? We're looking at CERN, um, the European Council for Nuclear Research, but in French, the letters come in a different order. Well, CERN is the organization. The actual thing we're looking at here is the LHC, the Large Hadron Collider. This is the single largest or the largest single machine in the world. This thing is huge. It's a ring. It's 27 kilometers long. And in this ring, they accelerate particles in both directions to very, very near the speed of light. And then they smash them together and they look at the smashings they have made with these very neat detectors. So here's one such detector. I believe this one is called Atlas. So this huge detector, yeah, huge machine going on here. For scale, you can see people with hard hats down here. Yeah, so this thing is gigantic. Just one part of this 27 kilometer long ring. Yeah, and they detect these collisions and they look at the pieces that come out. So here is an image from, I don't know if it was from this one, this particular detector, but yeah, here's an image. The kind of image that these things make. So it's a mess if you don't know what's going on. I kind of understand some of the things that's going on in this, but yeah, it's confusing. Anyhow, I will put a link to this video on these particle accelerators, well, specifically this one, and just the amazing things that they do here. So before I go on, well, let me go back to this real quick. The basic idea is, E equals mc squared. That was, the fourth paper from Einstein's miracle year. Energy and mass are equivalent. So the basic idea behind a particle accelerator is if you put enough energy into some particles and then you smack them together, some of that energy, which was just kinetic energy a moment before, can become the mass of new particles. So by putting a lot of kinetic energy into particles and smacking them together, new things can fly out. And then you detect them and you see what you've got. And if you're very, very clever, um, you can figure out something about the universe this way. So here's our formula for total energy E. So not just rest energy. Rest energy, E naught equals m naught c squared, is just the energy of a particle that's not moving. Total energy for a moving particle is this. So what will happen to the total energy E of a rest mass, m naught, as V approaches C? So what's going to happen to this whole thing as V starts getting closer to C? Well, what happens is as V gets closer to C, V squared over C squared, V squared over C squared starts getting closer to 1. So square root of 1 minus this thing that starts getting closer to 1 starts being the square root of 1 minus 1, which is the square root of 0, which is 0. So what's happening to your denominator is it's getting smaller and smaller. It's approaching 0. It will never actually get to 0. We've been telling you your whole life that you cannot divide by 0. Here's kind of a reason why. As we're getting closer and closer to 0 in the denominator, well, the total energy you need, or the total energy this particle has, starts getting bigger and bigger. So the energy approaches infinity. This is energy you had to put into the thing. So you can't actually put infinite energy into a particle. There's only so much energy in the universe. So this means that it would take an infinite amount of energy to accelerate a mass to the speed of light. And therefore, it can't be done because there isn't an infinite amount of energy. So that means nothing with mass can travel at the speed of light. Turns out that things that are massless, like photons, have to travel at the speed of light, but things that have mass cannot travel at the speed of light because you're not allowed to divide by 0. And I mentioned this in the one class. You're not allowed to divide by 0, but you are allowed to take the square root of negative numbers. That gives you an imaginary number, which is a totally valid kind of number. Imaginary number is a terrible name for these things. It's not that they don't exist. They too very much exist. In this particular case, I don't know if that has any physical reality. Yeah, so I don't know. Point is, you can't get something with mass up to the speed of light for this reason. So other relativistic weirdness. As things start moving faster and faster, from your point of view and your frame of reference, they're going to gain mass. So this would be the observed mass is equal to the rest mass of the thing, the mass it just has when it's sitting there, divided by this term. And because this term will always be less than 1, could be 1. If v is 0, then this term is 1. But as v starts getting closer to c, this term starts getting smaller and smaller. Your denominator gets smaller and smaller, which means your observed mass starts getting bigger. So not only does the thing appear to be more massive to you, the thing is more massive to you. So that's weird that things gain mass as they move fast. And remember from last year, our formula for momentum P equals mv. All right, well, if the mass is going up, we need a new formula for v. And finally, this last formula at the bottom, Galilean transformations no longer work. So what are Galilean transformations? That is with Paul the pitcher throwing baseballs on the back of the truck, and Alice is on the truck, and Billy's standing in the road, and Charlie's in a car going the other way. So that old-fashioned way of just adding the numbers together to get the what the velocity is in those different frames of references doesn't work. And when you get close to the speed of light, it doesn't work at all. Of course, because of the correspondence principle, if you're adding velocities and they are nowhere near the speed of light, it works perfectly fine. It's not 100% true, but it's very, very accurate. So, yeah, I'm not. If you look at this long enough, maybe you can figure out why. All right, I'll tell you. If both velocities are very small compared to the speed of light, then v1 times v2 will be very tiny compared to c squared, which means your denominator over here is 1 plus a very, very tiny number. So it's basically 1. It's really, really close to 1. So v1 plus v2 would just be add the two velocities together and then divide them by some number that's very, very close to 1, which isn't going to have a big effect on them. But once v1 and or v2 start getting close to the speed of light, then your denominator starts getting further and further away from 1, so dividing by it starts to matter more. So hopefully this video doesn't end up too long. So yeah, the LHC, the Large Hadron Collider. So it's going to accelerate a proton which has a rest mass of 938.3 mega electron volts per c squared. So the capital M means mega, which means million. So multiplied 938.3 times 10 to the 6th. But the weirder thing is that, yeah, I've given you a mass in terms of EV over c squared. Our usual units for mass are kilograms, and this is way different than kilograms. So I'll explain that in a second. Below that, if the proton is given a total energy of 6.5 TeV, tera electron volts, so 6.5 times 10 to the 12th. So our units of energy here are electron volts. We usually use joules. So yeah, you use different units when you're doing particle physics. So ultimately, we're going to try to figure out what is the velocity of the proton. So yeah, this is the thing with the units. Regular SI units are very awkward to use in situations like this. You can use them. You can use the mass of these things in kilograms. You can use C as 3 times 10 to the 8th meters per second squared. You can do a calculation and convert tera electron volts to joules. And as long as you're doing all the right units, it will work out fine. But they're not very handy. It's way easier to do these things with these special units that particle physicists use. Now, unfortunately, these things, it seems as though they are named purposely to confuse people who are not familiar with them. Once you actually use them, you get pretty fluent in it. It's not hard, but they are named a little bit weird. So V stands for volt. We'll get to that later, but a volt is a unit of electric potential. EV stands for electron volt, which is not the same kind of thing as a volt. A volt is electric potential, and EV is actually a unit of energy, so different kind of thing. So what an EV is if you put something with the charge of an electron through an electric potential, a voltage of 1 volt, you get 1 EV of energy. That's how that works. And then there are all the metric prefixes. So yeah, K, kilo electron volts, means 1,000. Capital M means mega, million, times 10 to the 6th. G means giga, so times 10 to the 9th, that's billion. And T means tera, so times 10 to the 12th, that's trillion. So you may have seen these things before if you were talking about hard drives and memory and things like that. Yeah, kilo, mega, giga, tera. After that comes peta, and I forget what the other ones are. But yeah, so all of these versions of EVs, they're all units of energy. So yeah, that kind of explains this one, why we're using TeVs instead of joules. But yeah, the very weird one, MEVs over c squared as units of mass. So if E equals mc squared, well, that means M equals E over c squared, which means you can have units of mass that are an energy divided by a velocity squared, in particular c squared. So you use this because it's way handier to use this kind of thing. So the mass of a proton, the correct way to say it would be 938.3 MeV per c squared, although in practice, you usually just truncate it and say the wrong thing, and everybody knows what you're talking about. So you would normally just say 938.3 MeV, even though it's more correct to say MeV per c squared, because MEVs, that's a unit of energy. MEVs over c squared, that's a unit of mass. So how do you do this stuff? So we're trying to figure out what is the velocity of the proton. So we're going to take our formula for total energy. We're going to do some algebra. Ultimately, we're going to solve for V. And this is the beauty of using units like this. So yeah, look at going from the right side of this up here to the right side of this. So the rest mass of a proton is 938.3 times 10 to the 6 EV per c squared. So that's m naught right here. And then right away it gets multiplied by c squared. So this, per c squared times c squared, the c squared part just cancels out. We're dividing by c squared, and then we're multiplying by c squared. So it just disappears, which means on the right side after that, you're going to have something in EVs divided by something in EVs. So energy divided by energy, and you'll just end up with just a pure number with no units. So you do that, you get this very small number. We're trying to solve for V, so you have to square it to get rid of the square root sign. You do some more algebra, subtract this from both sides, add v squared over c squared to both sides. So we're down to here, and then you have to take the square root of everything, and you end up with v is equal to point, and then a bunch of nines, 896, which means that this proton, this 6.5 tera electron volt proton, which means we've taken a proton and put it through a electric potential difference, a voltage of 6.5 trillion volts. So that's how much energy we've given this thing. It has gotten it up to 99.9999896% the speed of light. So very, very close to the speed of light. But of course, not the speed of light, because you can't get something with mass to go the speed of light. So basically, when you're not near the speed of light, if you put energy into a thing, almost all of that energy will become kinetic energy, and very little of it will become mass. And it just works that way until you start getting very close to the speed of light. Once you get closer and closer to the speed of light, and you're putting more and more energy into this thing, less and less of that energy is becoming kinetic energy. I mean, it still gets more kinetic energy, but less and less of it is becoming kinetic energy, and more of it is becoming the energy of mass. So, yeah, weird. So, more relativistic weirdness. How does the proton's mass compare to its rest mass when it is traveling at this number that is so very close to, but necessarily slightly less than 100% the speed of light? What's going to happen to the proton's mass? So here is your formula for relativistic mass. M, so the observed mass, is equal to the rest mass divided by this ugliness. So do the algebra, and m over m naught is going to be this. Well, we just figured out what the ugliness is. So you take 1 divided by this ugliness here, and you get 6,927, which means the proton is 6,927 times more massive when it's moving, when it has 6.5 tera electron volts of energy. It's almost 7,000 times more massive than when it's just sitting there, which again is really, really weird. And it's not just that it appears more massive. In your frame of reference, it is more massive. So craziness. So back to this idea. Derive an expression for velocity in terms of total energy. So what I'm saying is take this right here, E equals m naught c squared divided by the square root of 1 minus v squared over c squared. And derive an expression for velocity means solve all of this, get v by itself on one side. So you do a bunch of algebra. You do it very carefully. And when you're done, I mean, there's different ways to write this correctly, but here's one way where I have v is equal to something times c. So let's concentrate on this something. This something, the thing that's in the big parentheses here, will always be greater than or equal to 0. So it's allowed to not be moving, to have a velocity of 0, but it can be somewhere between 0 and something less than 1. So the fact that this term here, no matter how much energy is in the thing, will always be less than 1 is another way of saying you can't get something with mass to go the speed of light. So that's why. So it's like nails on a blackboard for a physics teacher to hear a student say, okay, well, what if you're going the speed of light? And then you say you can't actually go the speed of light. And then they say, okay, but what if you could? Well, you can't, because I know what happens as you get closer and closer to the speed of light. And give me any amount of energy in the universe, and I can tell you how close I can get any given mass to the speed of light, but you can't get it to the speed of light exactly. So that's it for this part of the slides. Hopefully you guys are finding this helpful, and, particle physics, some pretty crazy stuff. Hopefully you're finding it interesting.